The universe is 13.8 billion years old. Light travels at the fastest speed physics allows, so the farthest thing we could possibly see should sit 13.8 billion light-years away. It does not. The edge of the observable universe is 46.5 billion light-years away in every direction. The visible cosmos is more than 3 times wider than its age in light-years should ever permit. And the observable universe is not the whole universe. What lies beyond may be at least 75 times wider than everything we observe, maybe infinitely wider. Nobody knows, nobody ever can. The part of reality that light has had time to show us may be nothing more than a speck inside something we will never see, never reach, and never prove exists. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. Now, settle in, get yourself comfortable, let's begin. Every human being carries the same broken mental map of the cosmos. The universe is 13.8 billion years old. Light moves at 186,000 miles per second, the absolute speed limit of physics. Multiply speed by time, and you get distance. So the most distant thing we could ever detect should sit 13.8 billion light-years away. That number already feels staggering. It suggests a cosmos so enormous that the fastest phenomenon in nature would need the entire history of creation to cross it. The logic seems airtight. The universe had a beginning. Light has a fixed speed. The maximum observable distance should equal the age of the universe expressed in light years. Clean, simple, intuitive. The logic is wrong, not slightly wrong, not off by a rounding error or a matter of academic nuance. Wrong by a factor of more than 3. The observable universe does not extend 13.8 billion light-years from Earth to its farthest visible edge. It extends 46.5 billion light-years. In every direction, the full diameter stretches roughly 93 billion light-years across, a sphere of visible space so enormous that the number most people instinctively assume, a 13.8 billion, accounts for less than a third of the actual radius. The universe we can observe is vastly, measurably, confirmed by every major space mission larger than its own age in light-years would suggest. This is not a fringe claim. It is not a speculative hypothesis waiting for confirmation. It is an established measurement, verified by multiple independent methods, supported by decades of data from space-based observatories and ground-based surveys. The number 46.5 billion light-years represents the current comoving distance to the farthest signals we have ever received. The faint glow of the cosmic microwave background, the afterglow of the Big Bang itself. Every cosmological model consistent with observed data agrees on this figure within a margin of roughly 2%. The mismatch between the age of the universe and the radius of the observable universe is one of the most important facts in all of cosmology, and most people have never heard of it. So how does a universe that has existed for only 13.8 billion years manage to have a visible edge more than 3 times farther away than light should have been able to travel in that time? The answer demolishes the most basic assumption embedded in human intuition about distance and space. Space is not a fixed stage. It is not an unchanging container through which objects move like billiard balls on a table. Space itself has been expanding for the entire history of the cosmos. While light from the most distant sources was traveling toward us, the space between those sources and Earth was stretching. The photons kept moving at the speed of light through their local region of space, always, without exception. But the total distance they needed to cover kept growing beneath them, because the fabric of space itself was getting larger. By the time those ancient photons finally arrived at our telescopes, the objects that originally emitted them had been carried far beyond the distance that simple light travel time would predict. This is the first fracture in the ordinary mental map. Distance in cosmology does not work the way everyday experience teaches you to expect. And to understand why, you have to confront one of the strangest consequences of looking outward into space. Every observation you make of a distant object is also a look backward through time. The farther you see, the deeper into the past you are looking. The telescope is not merely a magnifying instrument, it is a time machine. When you glance at the sun on a clear afternoon, you are not seeing it as it exists at that precise moment. You are seeing it as it existed roughly 8 minutes ago, because sunlight takes approximately 8 minutes to cross the 93 million mile gap between the solar surface and your eyes. The sun you observe is always a slightly outdated version of the real thing. If the sun were to vanish without warning at this instant, you would continue to see it burning in the sky for another 8 minutes before the darkness arrived. For all practical purposes, 8 minutes is nothing. You would never notice the delay. But the principle behind it scales to distances where the delay becomes not just noticeable but universe-altering. The nearest star system beyond our own, Alpha Centauri, sits about 4.3 light-years from Earth. The light arriving from Alpha Centauri tonight departed that star system 4.3 years ago. You are seeing it as it was in the past, a frozen portrait carried to you by photons that have been crossing the interstellar void since before your last presidential election. If a planet orbiting Alpha Centauri were destroyed today, the flash of its destruction would not reach our telescopes for more than 4 years. Stretch the distance further. The center of our own galaxy, the Milky Way, lies roughly 26,000 light-years from Earth. The light arriving from the galactic core tonight began its journey 26,000 years ago, during the last ice age, when glaciers covered much of northern Europe and anatomically modern humans were painting animals on cave walls in France. The galactic center you observe through infrared telescopes is not the galactic center of today. It is an ancient version, frozen in the light of deep prehistory. Now leap beyond our galaxy entirely. The Andromeda Galaxy, our nearest large galactic neighbor, sits roughly 2.5 million light-years away. The photons that reveal Andromeda's spiral arms to a backyard telescope tonight began their journey 2.5 million years ago, when the genus Homo was just emerging on the plains of East Africa. The galaxy you see is not the Andromeda of this moment. It is the Andromeda of an epoch so distant that no human being existed to wonder about it. Whatever Andromeda looks like right now, whether new stars have ignited, whether a supernova has reshaped one of its arms, whether entire civilizations have risen and fallen on planets, orbiting its roughly 1 trillion stars, we will not know for another 2.5 million years, when the light from those events finally completes its crossing. This principle that looking far away means looking back in time does not stop at the nearest galaxies. It scales all the way to the edge of the observable universe. The farthest objects we can detect are not merely distant. They are distant and ancient simultaneously, separated from us by both space and time in quantities that make geological epochs look brief. Astronomers call this look-back time. It is not a metaphor or an approximation. It is a physical reality imposed by the finite speed of light combined with the finite age of the cosmos. Every astronomical image you have ever seen is a composite of different moments in history. When the Hubble Space Telescope or the James Webb Space Telescope produces a deep-field photograph, one of those breathtaking images showing thousands of galaxies scattered across a tiny patch of sky. Every galaxy in that image belongs to a different epoch. The nearest galaxies appear roughly as they are today. Galaxies a few billion light-years away appear as they were when the solar system was forming. The most distant smudges of light show galaxies as they were in the first billion years after the Big Bang, when the universe was a fraction of its current age and the cosmos looked nothing like it does now. The James Webb Space Telescope has pushed this time machine to extraordinary depths. In 2025, researchers confirmed a galaxy designated MOM Z14 as the most distant spectroscopically confirmed galaxy ever observed. It appears at a redshift of approximately 14.44, meaning the light we detect from it was emitted just 280 million years after the Big Bang. That light has been travelling for over 13.5 billion years. When those photons began their journey, the universe was barely 2% of its current age. Stars and galaxies were only just beginning to assemble from the primordial gas left over from the Big Bang. The cosmos was a darker, simpler, more violent place. And yet this galaxy was not the faint, fragile smudge that astronomers expected to find at such an extreme distance. It was bright, compact, and chemically enriched, far more developed than any model of early galaxy formation had predicted. Before the James Webb Space Telescope launched, theoretical frameworks suggested that galaxies this young should be dim, diffuse, and primitive, barely beginning to assemble their first generations of stars. MOM Z14 shattered that expectation. It looked like a galaxy that had no business existing so early in cosmic history, as though the universe had built structure faster and more efficiently than anyone thought possible. The discovery did not change the size of the observable universe, but it changed what the observable universe was telling us. Even the part we can see holds surprises we did not anticipate. But MOMS 14 is not 13.5 billion light-years away. That number represents only the look-back time, how long the light has been in transit. The actual present-day distance to MOMS 14, accounting for all the expansion that has occurred during those 13.5 billion years of travel, is approximately 36 billion light-years. The galaxy has been carried outward by the stretching of space, moving farther from us every moment since its light departed. We see it where it was, we cannot see where it is now, and where it is now is more than twice as far as the light travel time alone would suggest. This is not a peculiarity of one unusually distant galaxy. Every distant object in the cosmos tells the same story. The farther back in time you look, the greater the discrepancy between look-back time and actual current distance. A galaxy whose light has been travelling for 10 billion years does not sit 10 billion light-years away. It sits farther, because expansion has been stretching the space between us and that galaxy for the entire duration of the light's journey. A galaxy whose light has been travelling for 13 billion years is even more dramatically displaced. The most ancient light of all the cosmic microwave background, emitted approximately 13.8 billion years ago, comes from a surface that now sits approximately 45 billion light-years away, in every direction. Understanding the cosmic microwave background is essential to grasping why the observable universe is so much larger than its age implies. This radiation is the single most important signal in all of observational cosmology. It represents the oldest light in the universe, a relic from the moment when the cosmos first became transparent. Before that moment, the universe was a superheated plasma, a dense, seething fog of free electrons and protons, so tightly packed that photons could not travel more than a tiny distance before scattering off a charged particle. Light was trapped. The universe was opaque, as impenetrable to radiation as the interior of a star. No photon could escape, no signal could propagate. The cosmos was a glowing prison for its own light. Then, roughly 380,000 years after the Big Bang, expansion cooled the plasma below about 3,000 degrees. At that temperature, electrons slowed enough to be captured by protons, forming neutral hydrogen atoms for the first time. The charged particles that had been scattering photons vanished from the scene. Suddenly, space became transparent. Light was free. Photons that had been ricocheting endlessly through the plasma were released in every direction simultaneously, flooding the cosmos with radiation. That flood of light has been travelling ever since, crossing the expanding universe for almost the entire age of the cosmos, cooling from the blinding glow of a 3,000-degree fireball to the faint 2.725 degree Kelvin whisper we detect today. This cosmic microwave background was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey, who could not figure out why their antenna kept picking up a persistent, uniform hiss from every direction in the sky. They cleaned pigeon droppings from the antenna, checked every instrument, and eliminated every possible source of interference. The noise persisted. It came from everywhere, equally, without pause. Eventually, they realized they were hearing the afterglow of the Big Bang itself, the oldest signal in the universe, arriving at Earth from every direction because it was emitted from every point in the early cosmos simultaneously. In the decades since, 3 major space missions mapped this radiation in progressively finer detail. The Cosmic Background Explorer, launched in 1989, confirmed that the radiation matches a perfect thermal spectrum, exactly what theory predicted for the cooling afterglow of a hot, dense early universe. The Wilkinson Microwave Anisotropy Probe, launched in 2001, measured tiny temperature fluctuations in the cosmic microwave background, variations of only a few hundred thousandths of a degree from one patch of sky to another. These fluctuations encode the density differences that existed in the infant universe, the faint gravitational seeds from which all cosmic structure eventually grew. Slightly denser regions pulled in more matter over billions of years, eventually becoming galaxies and galaxy clusters. Slightly less dense regions emptied out, becoming the vast cosmic voids that dominate the universe's volume today. The Planck spacecraft, launched in 2009, refined these measurements further, producing the most detailed map of the cosmic microwave background ever created, and pinning down the age, composition, and geometry of the universe to extraordinary precision. Among the Planck mission's most important results is the precise measurement of the universe's spatial curvature. Combined with baryon acoustic oscillation data, Planck found the curvature parameter to be 0.001, plus or minus 0.002. In plain language, space is flat to within less than 0.5%. This measurement has enormous implications for the question of how large the universe really is, implications that will become clear before this story ends. For now, what matters is what the cosmic microwave background tells us about the mismatch between age and observable size. When the cosmic microwave background photons were released 380,000 years after the Big Bang, the matter that emitted them was not 45 billion light-years away from our current location. It was much, much closer, roughly 42 million light-years away, a tiny fraction of the present distance. The universe was far smaller and far denser. As those photons traveled across space for nearly 13.8 billion years, the universe expanded beneath them, stretching the distance between their origin and their destination by a factor of more than 1,000. The matter that emitted those photons was carried outward by expansion, receding from us at ever-increasing speeds, until it now sits at a co-moving distance of approximately 45 billion light-years. The photons themselves covered that expanding distance at the speed of light, always moving through their local patch of space at exactly 186,000 miles per second. But the accumulation of expansion over 13.4 billion years means they traversed a total distance vastly greater than either their travel time or their local speed would suggest in a static universe. This is the core of the mismatch. The observable universe has a radius of 46.5 billion light-years, not because light traveled that distance in 13.8 billion years through static space, but because space expanded while the light was in transit. The two numbers, age and radius, are disconnected because the universe is not a fixed container. It is a dynamic, stretching fabric, and the relationship between travel time and distance depends on how much stretching occurred during the journey. For the oldest light we can detect, the answer is an enormous amount. Scientists quantify this using a concept called co-moving distance. Co-moving distance is the distance between two objects measured at the present moment, with all the expansion that has accumulated since the Big Bang factored in. It answers the question: if you could freeze the entire universe at this instant and stretch a tape measure from Earth to a distant galaxy, how long would that tape need to be? For the surface of last scattering, where the cosmic microwave background originated, the co-moving distance is approximately 46.5 billion light-years. For the most distant confirmed galaxies, it ranges from roughly 30 to 40 billion light-years depending on their specific redshift. These are not theoretical projections or model-dependent guesses. They are real, measurable distances in the current universe, derived from observed redshifts combined with well-tested cosmological parameters. The observable universe, then, is a sphere with a co-moving radius of 46.5 billion light-years, centered on the observer. It is centered on Earth not because Earth is special, but because the observable universe is defined by the reach of light. Every observer everywhere in the cosmos sits at the center of their own observable sphere, defined by the maximum distance from which light has had time to reach their particular location. An alien astronomer in a galaxy 3 billion light-years away would have their own observable sphere of roughly the same size, centered on their position, overlapping with ours in some regions and extending into space that we can never observe. Every point in the universe is the center of its own observable cosmos. No location is privileged, no perspective is more complete than another. This deserves a moment of careful thought, because the implications are stranger and more important than they first appear. Consider an alien astronomer living in a galaxy 3 billion light-years from Earth. That astronomer has their own observable universe, a sphere of roughly the same radius as ours, approximately 46.5 billion light-years, centered on their position. Their sphere overlaps with ours across an enormous volume of shared space. Galaxies that we can see, they can see too, though from a different angle and at slightly different look-back times. The cosmic microwave background that bathes our sky also bathes theirs, arriving from the same era but from a slightly different shell of last scattering surface surrounding their location rather than ours. But here is what changes everything. Their observable sphere extends 3 billion light-years farther than ours in the direction away from Earth. In that direction, they can see galaxies whose light has never reached us, and never will galaxies that lie beyond our particle horizon, permanently outside our observable volume, invisible to every telescope humanity could ever build. Those galaxies are real. They contain stars, planets, perhaps civilizations of their own. They participate in the cosmic web, obey the same physics, and formed from the same primordial density fluctuations that seeded every structure in the cosmos. But from our position, they do not exist in any observational sense. No photon from those galaxies has arrived at Earth. No signal from them has crossed our horizon. They are part of the universe, but not part of our universe. Not part of the volume that light has had time to reveal to observers at our particular location. Now run the same logic in the opposite direction. Our observable sphere extends 3 billion light-years farther than theirs in the direction away from their galaxy. We can see objects that they cannot. Galaxies that are inside our horizon and outside theirs. Structures that are part of our observational reality, but invisible from their vantage point. If they have cosmologists, brilliant ones, with instruments far more sensitive than ours, those cosmologists have no way to learn about the part of our observable universe that falls outside their own. Their models of the cosmos are built from a different sample. Their map overlaps with ours but does not match it. Neither map is wrong. Neither is complete. Both are limited by the same fundamental constraint, the finite speed of light and the finite age of the cosmos applied from different locations. Now multiply this by every possible position in the universe. Every point in space has its own observable sphere. Every sphere overlaps with its neighbours but extends into unique territory that no other sphere can access. The total number of distinct observable spheres is not countable in any practical sense, because the universe is not a grid of discrete positions. It is a continuum. Every point has a horizon. Every horizon reveals a slightly different slice of the total cosmos. And no single horizon, not ours, not the alien astronomers, not any hypothetical observers anywhere in the universe encompasses the whole. This means that the observable universe is not a property of the cosmos. It is a property of the observer. The universe does not have an observable volume. It has an uncountable infinity of observable volumes, one for every possible position in space, each one centered on a different point, each one showing a different partial view of a reality that no single view can capture. The 93 billion light-year sphere we call the observable universe is not a feature of nature. It is a feature of where we happen to be standing. Move to a different location and the sphere shifts, revealing new regions while concealing others. The total reality, the complete set of everything that exists, is the union of all possible observable spheres, and that union is guaranteed to be larger than any individual sphere within it. How much larger depends on the size of the total universe, which is exactly the question that the rest of this story must confront. This leads to a distinction that most people never encounter, but that rewrites everything about cosmic size. The observable universe and the actual universe are not the same thing. The observable universe is defined by the reach of light. It is the volume of space from which photons have had time to travel to us since the Big Bang. Beyond that volume, there is almost certainly more space, more matter, more structure regions of the cosmos that look much like what we see in every direction, full of galaxies and stars and voids and filaments. We simply cannot see those regions because the light from them has not had enough time to reach us. The edge of the observable universe is not a wall. It is not a physical barrier where space ends or matter vanishes or the laws of physics change. It is a horizon, exactly like the horizon you see when standing on a vast open plain. Land continues beyond the horizon. You simply cannot see it from where you stand. And in the case of the cosmos, expansion is carrying much of that hidden land away from you faster than new light from it can arrive. This distinction between the observable universe and the total universe is the single most important concept for understanding why the cosmos is far bigger than almost anyone imagines. When a documentary or textbook says the universe is 93 billion light-years across, it is describing only the observable part, the fraction that light has had time to reveal. The actual universe extends beyond that boundary, and the amount by which it extends may be staggering. Determining how much larger the total universe might be requires measurements of cosmic geometry, the physics of inflation, and data that pushes our instruments to their absolute limits. But before asking what lies beyond the observable edge, there is an even more disorienting consequence of expansion that demands attention. The mismatch between age and observable size is not just a historical artifact of 13.8 billion years of past expansion. It is an active, ongoing, accelerating process. Space is not merely expanding, the rate of expansion is increasing. Every second, the distances between distant galaxies grow a little faster than they did the second before. This acceleration, driven by a mysterious component that makes up roughly 68% of the total energy content of the universe, means that the relationship between what we can see and what we can reach is not fixed. It is changing, and it is changing in a direction that makes the universe progressively less accessible, less knowable, and less navigable with every passing moment. Expansion made the observable universe 3 times larger than its age in light years, but expansion does more than stretch distances. It builds walls that light can never cross. Understanding how those walls form, where they sit, and what they permanently hide from observation requires confronting the full machinery of how space itself moves, and how it is beginning to outrun the light that carries every piece of information we will ever receive about the cosmos. There is a question that seems so obvious it feels almost embarrassing to ask. If the universe is expanding, what is it expanding into? The question makes perfect sense from the perspective of everyday experience. When a balloon inflates, it expands into the air surrounding it. When a city grows, it sprawls into the countryside beyond its edges. Expansion, in every context humans encounter in daily life, means something is getting bigger inside a larger container. So the universe must be expanding into some kind of outer space, some void beyond the boundary, some room in which the cosmos is gradually filling up. The answer is that the question itself is built on an assumption that does not apply. The universe is not expanding into anything. There is no external space beyond the universe waiting to be filled. Space itself, the very fabric in which all matter, energy, and light exist, is the thing doing the expanding. The universe is not a balloon inflating inside a room. The universe is the room, and the room is getting larger on its own, everywhere, simultaneously, without needing anything outside itself to expand into. This is not a philosophical dodge or a linguistic trick. It is a description of how general relativity describes the geometry of space-time, and it has been confirmed by every major cosmological observation of the past century. Understanding this distinction is essential to grasping how the universe can be far bigger than its age suggests, and why much of it may be permanently beyond our reach. Expansion does not mean galaxies are flying through space away from each other, propelled by some ancient explosion. It means the distances between galaxies are increasing, because the space between them is growing. The galaxies themselves are mostly sitting still relative to their local patch of space. They are not rockets. They are not projectiles launched by the Big Bang. They are embedded in a fabric that stretches, and as the fabric stretches, the gaps between objects widen. Imagine a loaf of raisin bread rising in an oven. Before the dough begins to rise, the raisins sit relatively close together, embedded throughout the dough at various positions. As the bread expands, every raisin moves away from every other raisin, not because the raisins are crawling through the dough, but because the dough between them is swelling. A raisin near the center of the loaf sees every other raisin receding. A raisin near the edge sees exactly the same thing, all its neighbors pulling away. No raisin occupies a special position. No raisin is at the center of the expansion. The expansion is happening everywhere in the dough simultaneously. And here is the critical detail. Raisins that are farther apart separate faster, because there is more dough between them to expand. 2 raisins separated by 1 centimeter of dough see that centimeter grow by a small amount. two raisins separated by 10 centimeters of dough. See those 10 centimeters grow by 10 times as much in the same period. Distance determines recession speed. The farther apart two objects are, the faster they appear to move away from each other. This relationship, recession velocity increasing with distance, is exactly what astronomers observe in the real universe. In the 1920s, Edwin Hubble and his contemporaries, building on earlier redshift observations by Vesto Slipher and theoretical predictions by Georges Lemaître, discovered that distant galaxies are systematically moving away from us, and that the farther a galaxy is, the faster it recedes. This pattern, now called the Hubble flow, is not the result of galaxies being hurled outward by an explosion. It is the signature of expanding space, the cosmic dough rising in every direction at once. The rate of this expansion is described by the Hubble constant, a number that tells you how fast recession velocity increases with distance. For every megaparsec of distance, roughly 3.26 million light-years, the recession velocity increases by a fixed amount. Current measurements place this value somewhere between 67 and 73 kilometers per second per megaparsec, depending on which method is used to measure it. This means that a galaxy 1 megaparsec away recedes at roughly 70 kilometers per second. A galaxy 2 megaparsecs away recedes at roughly 140. A galaxy 10 megaparsecs away recedes at 700. The relationship is linear, at least over the range of distances where this simplified version of the law applies. Distance and recession velocity are directly proportional. Now extend that linear relationship outward, far beyond the nearby galaxies Hubble originally studied, toward the most distant reaches of the observable universe. If recession velocity increases with distance, there must exist a distance at which the recession velocity equals the speed of light. And beyond that distance, the recession velocity exceeds the speed of light. This threshold is called the Hubble radius, and it sits at approximately 14 billion light-years from Earth. Everything beyond the Hubble radius is currently receding from us faster than light. This sounds like it should be impossible. Einstein's special theory of relativity forbids any object from traveling through space faster than the speed of light. No spaceship, no particle, no signal of any kind can exceed 186,000 miles per second relative to the space through which it moves. This speed limit is absolute, fundamental, and unbreakable. So how can galaxies beyond the Hubble radius recede faster than light without violating relativity? The answer returns to the distinction between motion through space and expansion of space. No galaxy is moving through its local patch of space at superluminal velocity. Each galaxy is essentially at rest relative to the space surrounding it, drifting gently at a few hundred kilometers per second at most. What is happening is that the space between us and that galaxy is expanding so rapidly that the total effect accumulated across billions of light-years of stretching fabric produces a recession velocity that exceeds the speed of light. Relativity forbids objects from traveling through space faster than light. It does not forbid space itself from expanding at any rate whatsoever. There is no speed limit on the growth of the cosmic fabric. The restriction applies to motion within the fabric, not to the behavior of the fabric itself. This means that right now, today, at this moment, the overwhelming majority of the observable universe is receding from us faster than light. Every galaxy beyond the Hubble radius of 14 billion light-years is moving away superluminally. The cosmic microwave background, which originated from a surface now 46.5 billion light-years away, is receding at more than 3 times the speed of light. We can still see these objects. Their ancient light reached us before the expansion carried them beyond the Hubble radius. But the objects themselves, as they exist today, are racing away from us at velocities that no signal we send could ever overcome. They are visible in our past, but unreachable in our future. This is where expansion begins to feel less like a technical detail and more like a sentence. The universe is not just large, it is actively making itself less accessible, and the force accelerating this process is the single most abundant and least understood component of the cosmos. In 1998, 2 independent research teams shattered a foundational expectation of cosmology. The teams, led by Saul Perlmutter on one side and Brian Schmidt and Adam Rees on the other, were studying distant Type 1a supernovae, a class of exploding star whose intrinsic brightness is well understood. By comparing how bright these supernovae appeared in telescopes to how bright they should be at their measured distances, the teams could determine whether the expansion of the universe was slowing down, as virtually every cosmologist expected. Gravity pulls matter together. In a universe filled with matter, gravity should gradually decelerate the expansion set in motion by the Big Bang. The question was not whether expansion was slowing, but by how much. The expectation of deceleration was not merely a hunch. It was a consequence of the most basic feature of gravity as described by general relativity. Mass attracts mass. Every galaxy in the universe gravitationally pulls on every other galaxy, and that collective pull should act as a cosmic brake, gradually reducing the expansion rate over time. The only open question was the magnitude of the braking. If the universe contained enough matter, the deceleration would eventually halt expansion entirely and reverse it, leading to a collapse sometimes called the Big Crunch, a mirror image of the Big Bang, with the universe contracting back to a singularity. If the universe contained less matter, expansion would slow but never quite stop, and the cosmos would coast outward forever at a diminishing rate. Either way, gravity was supposed to dominate. The expansion that began with the Big Bang was expected to be a decelerating expansion, with the rate of stretching decreasing over time as matter pulled everything back toward everything else. This was not just an assumption, it was embedded in the mathematics of general relativity. The Friedmann equations, which describe how the expansion rate evolves over time, include terms for matter density, radiation density, and spatial curvature. In every realistic model that included only matter and radiation, the two components that cosmologists knew about in the mid-1990s, the expansion rate decreased with time. Period. The equations left no room for acceleration unless you added a term that most physicists considered a relic of history: Einstein's cosmological constant, a mathematical placeholder he had introduced in 1917 to keep the universe static and later retracted, calling it his greatest blunder. So when the two supernova teams independently reported that distant Type 1a supernovae were dimmer than expected, meaning they were farther away than decelerating models predicted, the result was not merely surprising, it was physically disorienting. The data did not just say that gravity was losing the tug-of-war, it said there was no tug-of-war at all. Something was pushing. Something was accelerating the expansion of the universe against the combined gravitational attraction of every particle of matter in the cosmos. The reaction within the scientific community was one of genuine shock. Saul Perlmutter later described the result as feeling like throwing a ball into the air and watching it fly upward faster and faster instead of falling back to your hand. Both teams double-checked their data obsessively before publishing. They searched for systematic errors. They considered whether dust between galaxies might be dimming the supernovae, mimicking greater distance. They tested whether Type 1a supernovae at high redshift might be intrinsically different from nearby ones, producing less light. Every alternative explanation was examined and ruled out. The two teams, using different supernovae, different telescopes, and in different analysis methods, arrived at the same conclusion independently. The result held. The universe was accelerating. The mysterious force behind this acceleration was given a name: dark energy. Within a few years of the discovery, dark energy transformed from a speculative idea into the dominant component of the cosmos. The numbers were extraordinary and remain so today. Roughly 68% of the total energy content of the universe is dark energy. Only about 27% is matter, and most of that is dark matter, the invisible scaffolding that holds galaxies together, but has never been directly detected in any laboratory. Ordinary matter, atoms, stars, planets, people, everything that chemistry and biology are made of, accounts for a mere 5% of the cosmic energy budget. The universe is governed overwhelmingly by a force we cannot see, cannot detect directly, and do not understand. The discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, recognition that the most abundant component of reality had been entirely unknown to science until the closing years of the 20th century. The simplest theoretical model for dark energy treats it as a cosmological constant, a fixed energy density built into the fabric of space itself. In this picture, Every cubic meter of empty space contains a tiny but constant amount of dark energy. As space expands and the volume increases, the total amount of dark energy grows, because more space means more of this built-in energy. Matter, by contrast, thins out as space expands. The same amount of mass spreads over a larger volume, reducing its density. Over cosmic time, dark energy inevitably wins the tug-of-war against gravity. The expansion accelerates, not because dark energy is getting stronger per unit volume, but because matter is getting weaker per unit volume, while dark energy holds steady. For over 2 decades, this cosmological constant model fit the data remarkably well. It formed one of the pillars of the standard model of cosmology, the lambda cold dark matter framework that describes a universe made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy behaving as a constant. This framework passed test after test, matching observations of the cosmic microwave background, the distribution of galaxies on large scales, the abundance of light elements produced in the first minutes after the Big Bang, and the accelerating expansion revealed by supernovae. Lambda cold dark matter became the consensus model of the cosmos, not because it was elegant. It requires 2 enormous unknown components, dark matter and dark energy, whose natures remain completely mysterious, but because it worked. Then the cracks appeared. The most prominent crack is called the Hubble tension, and as of the mid-2020s, it remains unresolved. When scientists use the cosmic microwave background to infer the expansion rate, effectively running the physics of the early universe forward through time and predicting what the Hubble constant should be today, they get a value of approximately 67 kilometers per second per megaparsec. When scientists use local observations, Cepheid variable stars, type 1a supernovae, and other distance indicators, in the nearby universe, they measure a value of approximately 73 kilometers per second per megaparsec. Both measurements are extraordinarily precise. Both have been checked, rechecked, and refined with improved data. The disagreement between them has reached a statistical significance of roughly 5 sigma, meaning there is less than a 1 in a million chance that the discrepancy is a random fluke. The James Webb Space Telescope was expected to resolve this tension. Its sharper resolution and greater sensitivity allowed researchers to remeasure the distance indicators with unprecedented accuracy, eliminating potential sources of error such as stellar crowding and dust contamination. Some teams, notably the group led by Wendy Friedman, reported measurements using different stellar indicators that landed closer to 69 or 70 kilometers per second per megaparsec, potentially easing the tension. But other teams, particularly those using Cepheid-calibrated supernovae, continued to find values near 73, ruling out observational errors at high confidence. As of 2026, the Hubble tension has not been resolved. It persists across multiple independent measurement methods and datasets. Something about our understanding of cosmic expansion is incomplete. The depth of this crisis is difficult to overstate. The Hubble constant is not just one number among many in cosmology. It is the number from which nearly every other cosmological measurement is derived. It determines the age of the universe. A faster expansion rate implies a younger cosmos, because the universe reached its current size in less time. It determines the distances to remote galaxies, because distance is calculated from redshift using the expansion rate. It determines the density of dark energy, because the acceleration of expansion depends on the balance between dark energy and matter. Change the Hubble constant by even a few percent, and the entire cosmological framework shifts like a house built on unsteady ground. What makes the tension so stubborn is that both sides of the disagreement are internally consistent and extraordinarily precise. The cosmic microwave background measurement from Planck is not a rough estimate. It is a calculation derived from the most detailed map of the early universe ever produced, using physics that has been tested and confirmed across multiple independent datasets. The local measurement from supernovae and Cepheid stars is not a rough estimate either. It is based on a carefully constructed distance ladder, calibrated step by step from geometric parallax measurements in our own galaxy outward to supernovae in distant galaxies, with every rung of the ladder scrutinized for systematic error. The disagreement means one of several things, and none of them are comfortable. Either one or both measurements contain a subtle, undetected systematic error that has survived years of rigorous checking. Or the standard cosmological model lambda cold dark matter is missing a piece. Perhaps there was an additional burst of expansion in the early universe that the model does not account for. Perhaps dark energy behaves differently at different epochs. Perhaps new particles or forces operated in the first moments after the Big Bang, altering the expansion history in ways that show up as a discrepancy between early universe and late universe measurements. Each of these possibilities would require revising fundamental aspects of physics. None has been confirmed. All remain on the table. The Hubble tension has become the defining puzzle of 21st century cosmology. It sits at the intersection of observation and theory, daring physicists to find the crack in either their data or their models. And it feeds directly into the most consequential implication of expansion. If we do not fully understand how fast the universe is growing, we do not fully understand the boundaries that expansion creates. If the Hubble tension represents one kind of crack in the standard model, recent results from the Dark Energy Spectroscopic Instrument represent another. This international project, managed by the Lawrence Berkeley National Laboratory, has created the largest three-dimensional map of the universe ever produced, measuring redshifts for millions of galaxies and tracing the expansion history of the cosmos over the past 11 billion years. In March of 2025, the collaboration released results that, when combined with data from the cosmic microwave background, supernovae, and gravitational lensing, showed hints that dark energy may not be a constant after all. The data suggest that the influence of dark energy may be weakening over time, that the equation of state describing dark energy's behavior is not fixed but evolving. This is a finding that, if confirmed, would fundamentally alter our picture of cosmic expansion. A cosmological constant is simple: the same energy density everywhere, forever, unchanging. Evolving dark energy is something entirely different. It could be a dynamic field that varies across space and time, growing stronger or weaker depending on cosmic conditions. It could mean that the acceleration of expansion is not permanent, that it might slow, stop, or even reverse in the far future. The Dark Energy Spectroscopic Instrument results have not yet reached the 5 sigma threshold that physics demands for a discovery claim. The hints are suggestive, not definitive, but they add to a growing picture in which the expansion of the universe is more complicated, more uncertain, and more surprising than the standard model assumed. What makes these uncertainties so unsettling is that the expansion rate governs nearly everything else in cosmology. The age of the universe, the distances to remote galaxies, the size of the observable sphere, the rate at which structures form, the future fate of the cosmos. All of these depend sensitively on how fast space is expanding and how that rate has changed over time. If the expansion rate is wrong by even a few percent, the entire cosmological framework shifts. Distances change, ages change, the history of structure formation changes. Even the relationship between what we can see and what we can reach changes in ways that cascade through every branch of astrophysics. The universe's expansion also creates a subtlety that is easy to overlook but essential to understanding cosmic distances. When astronomers quote the distance to a remote galaxy, say 30 billion light-years, they are quoting the co-moving distance, the distance measured at the present moment, with all accumulated expansion included. But that galaxy was not 30 billion light-years away when it emitted the light we now detect. It was much closer. The light did not need to cross 30 billion light-years of static space. It only needed to stay ahead of the expansion, and for most of cosmic history, it did. The photons we receive from distant galaxies were emitted when those galaxies were close enough for their light to begin reaching us. During the journey, expansion stretched the space behind the photons, increasing the total distance between source and observer. By the time the light arrives, the source has been carried far beyond the distance the photons actually traversed. The co-moving distance is the cumulative result of this ongoing stretching, not the distance the light travelled, but the distance the source has reached by the time the light arrives. This creates a deeply counterintuitive situation. Galaxies that are currently beyond the Hubble radius, receding faster than light, can still be visible to us if their light was emitted long ago when they were within the Hubble radius. The light was emitted from a closer position, entered our observable sphere, and has been travelling toward us ever since, even as the source was carried farther and farther away. We see these galaxies not as they are now, but as they were when they were much nearer, in a younger, smaller, denser universe. The image we detect is a fossil, a record of what that patch of space looked like billions of years ago, preserved in photons that have been crossing an expanding cosmos ever since. This fossil light effect is so counterintuitive that it deserves a concrete example, because the mechanism behind it is the key to understanding everything that follows about cosmic horizons. Consider a galaxy that emitted light roughly 13 billion years ago, when the universe was less than 1 billion years old. At the moment that galaxy released its photons, it was not 13 billion light-years away from the patch of space that would eventually become our solar system. It was much closer, perhaps 3 billion light-years, because the universe was far smaller and denser at that time. The photons left the galaxy and began crossing the intervening space at the speed of light. They did not need to traverse 13 billion light-years of static void. They only needed to cross the relatively modest distance that existed at the moment of emission, and then keep moving as space expanded beneath them. Here is where the critical detail enters. During the first several billion years of the photon's journey, the universe was decelerating. Matter was dense enough that gravity was still winning the contest against expansion, gradually slowing the rate at which space stretched. In a decelerating universe, photons can make steady progress. Even though the distance ahead of them is growing, it is growing slowly enough that the photons gain ground. The remaining distance between the photons and their destination shrinks with every passing moment, because the photons are crossing space faster than expansion is creating new space ahead of them. During this early phase, the galaxy that emitted the light was being carried outward by expansion, moving farther from the photon's destination with every passing moment. At some point during the journey, the cumulative expansion pushed the galaxy beyond the Hubble radius. Its recession velocity, relative to us, exceeded the speed of light. From that moment forward, the galaxy was moving away from us superluminally. If you froze the universe at that instant and asked whether the photons could still reach us, the naive answer would be no. Their source is receding faster than light, so they should be swept backward, carried away from us by the expanding space. But the photons were not at the galaxy anymore. They were already billions of light-years ahead of it, deep in transit, crossing space that was expanding more slowly than the space near the galaxy. The Hubble radius is not a single fixed boundary that a photon either crosses or does not. It is a distance that changes over time as the expansion rate evolves, and the photons, which began their journey well inside the Hubble radius, remained in regions of space where the local recession velocity was still subluminal, even as the source behind them was swept beyond it. The photons kept moving forward, 1 light second per second through their local space, crossing region after region that was expanding, but not fast enough to stop them. Eventually, those photons entered regions close enough to us that the recession velocity of the space around them dropped well below the speed of light. The remaining distance shrank rapidly. The photons arrived at Earth, carrying an image of a galaxy as it appeared 13 billion years ago, in a younger, smaller, more compact cosmos. The galaxy itself, meanwhile, has been carried by expansion to a current distance of perhaps 30 billion light-years. It is receding from us at more than twice the speed of light. No signal we send today could ever reach it, but its ancient light, emitted from a much closer position in a much smaller universe, completed the crossing before expansion could prevent it. This is not an edge case. It is the standard story for the majority of galaxies visible in deep-field images. Most of them emitted their light from positions well inside the Hubble radius of their era, and most of them now sit far beyond the current Hubble radius. We see their past selves, frozen in photons that won a race against expansion billions of years ago. The universe is full of these ghost portraits, images of objects that are no longer where we see them, and in many cases can never be contacted again. Every deep-field photograph is a gallery of objects that have already slipped beyond the reach of any future signal. The expansion of space also stretches the light itself. Photons traveling through expanding space have their wavelengths pulled longer, shifting them toward the red end of the electromagnetic spectrum. This is cosmological redshift, distinct from the Doppler shift caused by motion through space. The amount of redshift directly encodes how much the universe has expanded since the light was emitted. A galaxy observed at a redshift of 1 has had its light stretched by a factor of 2, meaning the universe has doubled in size since that light began its journey. A galaxy at a redshift of 10 has had its light stretched by a factor of 11, The cosmic microwave background, observed at a redshift of approximately 1100, has been stretched by a factor of roughly 1100, its original wavelength, corresponding to visible orange light from a 3000-degree surface, has been stretched into the microwave range, invisible to the naked eye but detectable by radio receivers and specialized satellite instruments. Redshift is the primary tool astronomers use to measure cosmic distances. By observing how much a galaxy's light has been stretched, scientists can determine how much expansion has occurred since the photons were emitted, and from that, using well-tested cosmological models, they can calculate both the look-back time and the co-moving distance to the source. This is how the observable universe was measured to be 93 billion light-years across. It is how the distances to the most remote galaxies are determined, and it is how the Hubble constant is calibrated by comparing redshift to distance for objects at various ranges and extracting the expansion rate that best fits the observations. But there is something the expansion rate reveals that transcends the mechanics of stretching light and growing distances. Expansion is not merely inflating the universe, it is creating permanent divisions within it. If the universe were expanding at a constant rate, or decelerating, there would be no hard limit on what we could eventually see. Given enough time, light from ever more distant regions would continue arriving, gradually expanding our observable horizon. The map would grow, slowly but without limit. Every region of the cosmos would eventually come into causal contact with every other region, connected by photons that had enough time to cross the intervening space. Accelerating expansion changes this completely. When expansion accelerates, the stretching of space overtakes the progress of light. Photons emitted today from sufficiently distant galaxies will never reach us, no matter how long we wait, because the space between us and those galaxies is growing faster than the photons can cross it. This creates a boundary, not a physical wall, not a barrier made of matter or energy, but a causal limit imposed by the geometry of expanding space-time. Beyond this boundary, events happening right now are permanently disconnected from our future. Light from those events will travel toward us at the full speed of light through its local space, but the expansion beneath it will stretch the remaining distance faster than the photons can close the gap. The light will chase us forever and never arrive. This boundary has a name. It is called the cosmic event horizon, and its existence means that the observable universe, as vast as it already is, does not represent the limit of what existed in the past, but rather the limit of what will ever be accessible in the future. The observable universe will never grow to include everything. Instead, as acceleration continues, the fraction of the cosmos we can interact with will shrink. The Hubble tension tells us we may not fully understand the expansion rate. The dark energy spectroscopic instrument results tell us dark energy itself may be changing, and both uncertainties feed directly into the most consequential implication of cosmic expansion: the existence of horizons that divide the universe into the part we can know and the part we never will. These horizons are not hypothetical. They are not projections of distant future physics. They exist right now at measurable distances, defining the boundaries of accessible reality at this very moment. Understanding what they are, where they sit, and what they permanently hide requires confronting the full structure of cosmic horizons and the staggering fraction of the visible universe that is already lost. Stand on the shore of a vast ocean at dusk. The water stretches outward until it seems to meet the sky at a clean, sharp line. That line is the horizon. You know, without needing to be told, that the ocean does not end there. Ships that sail beyond the horizon do not fall off the edge of the world. Water continues past the point where your eyes can no longer follow it. The horizon is not a wall. It is not a physical barrier that stops the ocean from existing. It is a limitation imposed by the geometry of Earth's curved surface and the fixed height of your eyes above the water. Move to a hilltop, and the horizon shifts outward. Climb a tower, and it shifts farther still. The boundary is real. It defines what you can see from where you stand, but it says nothing about what exists beyond it. The ocean goes on. You simply cannot watch it from here. The universe has horizons too. They operate on different principles, the speed of light and the age of cosmic time, rather than the curvature of the ground, but they share the same essential character. They mark the boundary between what is accessible and what is not. They are real, measurable limits that constrain what any observer can detect, reach, or influence. And like the ocean horizon, they say nothing definitive about what lies beyond. The cosmos almost certainly continues past its horizons. It simply refuses to show us. But cosmic horizons differ from terrestrial ones in a critical way. Standing on a shoreline, you can walk forward. You can sail toward the horizon, and as you approach it, it recedes ahead of you, always staying the same distance away, always revealing new water beyond. You are never trapped. The horizon limits your view, but never your movement. The cosmic horizons are not so generous. Some of them can never be reached, no matter how fast you travel, no matter how long you wait, no matter what technology you develop. They are permanent, and in an accelerating universe, they are closing in. The first and most familiar cosmic horizon is the particle horizon. This defines the edge of the observable universe, the maximum distance from which light or any other signal has had time to reach an observer since the Big Bang. The particle horizon exists because the universe has a finite age. Light travels at a fixed speed. In 13.8 billion years, there is only so far a photon can travel, even accounting for the expansion of space that stretches the total distance covered. The particle horizon sits at a moving distance of approximately 46.5 billion light-years in every direction. Everything inside this sphere is, in principle, observable. Everything outside it has not yet had time to send signals that could reach us. The particle horizon is not static. It grows over time, because every passing second allows light from slightly more distant regions to complete its journey. Tomorrow, Earth's particle horizon will be a little larger than it is today. A year from now, slightly larger still. In a purely decelerating universe, one where expansion gradually slows, the particle horizon would grow without limit. Given enough time, light from every corner of the cosmos would eventually arrive, and the observable universe would expand to encompass everything that exists. Every galaxy, every star, every atom would eventually come into view. The map would be complete. We do not live in that kind of universe. We live in one where expansion is accelerating, and this changes everything about what the particle horizon means for the future. The second cosmic horizon, less well known but far more consequential, is the cosmic event horizon. This boundary does not define what we have already seen. It defines what we will ever be able to see from this moment forward. It answers a different question from the particle horizon. The particle horizon asks, from how far away has light had time to reach us since the universe began? The cosmic event horizon asks, from how far away can light emitted right now, at this instant, eventually reach us, given all the future expansion that will occur while that light is in transit? The answer is approximately 16 billion light-years. That is the current distance of the cosmic event horizon. If an event occurs right now at a location less than 16 billion light-years away, the signal from that event will eventually reach Earth, though it may take billions or even tens of billions of years to arrive, because the light must fight against the expansion of space for the entire journey. But if an event occurs right now at a location more than 16 billion light-years away, no signal from that event will ever reach us. The expansion of space between the source and Earth will grow faster than the light can cross it. The photons will travel at the full speed of light through their local space, always, without exception, but the remaining distance will stretch faster than they can close it. They will chase us across an expanding cosmos and never arrive. The cosmic event horizon is not the same as the Hubble radius, though the two are related and often confused. The Hubble radius marks the distance at which the recession velocity of galaxies equals the speed of light, approximately 14 billion light-years. Everything beyond the Hubble radius is currently receding superluminally. But the Hubble radius is not a permanent barrier. Because the Hubble constant changes over time despite its name, it is not truly constant. The Hubble radius shifts. Some galaxies that are currently beyond the Hubble radius were once inside it, and vice versa. Light can cross the Hubble radius under certain conditions, entering the sphere of subluminal recession even if it was emitted from beyond it. The Hubble radius is a snapshot, a momentary boundary defined by the current expansion rate. The cosmic event horizon is more fundamental. It accounts not just for the current expansion rate, but for all future expansion, the entire trajectory of cosmic growth from now until the end of time. It integrates the total stretching of space that will ever occur and asks whether a photon emitted today from a given distance can outrun that cumulative stretching. For distances under 16 billion light-years, the answer is yes. For distances over 16 billion light-years, the answer is no, not now, not ever. To understand what this means in practical terms, think of a candle placed on a conveyor belt that moves away from you. If the belt moves slowly, the light from the candle reaches your eyes without difficulty. If the belt accelerates, there comes a point where the belt carries the candle away faster than the light can bridge the growing gap between you. The candle still burns, the light still travels at full speed, but the distance between you and the candle grows faster than the light can close it. The candle vanishes from your world, not because it stopped existing, but because the space between you and the flame is being manufactured faster than the light can cross it. The cosmic event horizon is the distance at which the conveyor belt of expanding space wins permanently. Now comes the devastating arithmetic. The observable universe, the sphere defined by the particle horizon, has a co-moving radius of 46.5 billion light-years. The cosmic event horizon sits at roughly 16 billion light-years. Everything between 16 billion and 46.5 billion light-years away is visible but permanently unreachable. We can see these regions because their ancient light, emitted billions of years ago from much closer positions, has already completed its journey to Earth. But any light those regions emit today will never reach us. Any signal we send toward them will never arrive. They are in our past, but not in our future. They are ghosts, visible, detectable, photographable, but causally disconnected from us from this moment forward. The fraction of the observable universe that falls into this ghost category is staggering. By volume, roughly 97% of the observable universe lies beyond the cosmic event horizon. By galaxy count, approximately 94% of the galaxies we can currently observe are already permanently out of causal contact with us. Of the hundreds of billions of galaxies visible in our deepest surveys, the overwhelming majority exist in regions of space that are receding superluminally, emitting light that will never reach us, evolving in ways we will never learn about, hosting events we will never detect. They are visible relics of a younger, smaller, more connected cosmos, a universe in which those regions were close enough for their light to begin reaching us. That universe no longer exists. The connections that allowed their light to arrive were severed by accelerating expansion, one by one, over billions of years. To feel the weight of this, consider what it means for specific objects you can photograph tonight. The Coma Cluster, one of the richest concentrations of galaxies in our cosmic neighborhood, sits roughly 320 million light-years away. It is well inside the cosmic event horizon. Signals we send today could, in principle, reach it. Light it emits today will reach us. The Coma Cluster is still part of our causal future. We are connected to it, albeit by a thread of photons that will take hundreds of millions of years to arrive. Now look farther. The galaxy cluster Abell 2744, one of the most massive structures ever observed, sits approximately 4 billion light-years away. It is already receding at a significant fraction of the speed of light, but it remains inside the cosmic event horizon. Light it emits today will eventually reach us, not for billions of years, but eventually. We are still connected, however tenuously. Now look to the galaxies in the Hubble ultra-deep field. Those faint smudges of light, each one a collection of billions of stars, sit at moving distances of 20, 30, even 40 billion light-years. The light we see from them was emitted when the universe was young, when those galaxies were far closer. But the galaxies themselves, as they exist right now at this moment, are deep beyond the cosmic event horizon. Light they emit today will never reach us. Light we send toward them will never arrive. If there are civilizations in those galaxies, beings with telescopes and questions and a desire to understand the cosmos, they are as permanently isolated from us as if they existed in a separate universe. We can see the places where they might live. We can study the conditions that prevailed when those galaxies were young. But we will never know what became of them. We will never exchange a single photon with them from this moment forward. There is something uniquely disquieting about this. These are not hypothetical galaxies in some theoretical model. They are real objects in real photographs, captured by real instruments. You can find the Hubble Ultra Deep Field image on the internet right now, and look at galaxies that are already causally gone. You are looking at a photograph of the permanent past objects whose light arrived as a record of what once was, delivered across a bridge of expanding space that has since collapsed behind it. The photograph is an artifact of a connection that no longer exists, like a letter received from someone who has already moved to an address beyond any postal route. This disconnection is not limited to the most distant objects. It extends to the vast majority of the observable universe. Consider the cosmic microwave background itself, the radiation that forms the boundary of our observable sphere. That radiation was emitted from matter that now sits approximately 45 billion light-years away. That matter, whatever it has become, galaxies, voids, structures we cannot imagine, is receding from us at more than 3 times the speed of light. Any signal it sends now will never reach us. Any signal we send toward it will never arrive. The very matter whose ancient light defines our observable universe is itself permanently beyond our reach. This means that every measurement we have ever made of the cosmic microwave background, every temperature fluctuation, every polarization pattern, every constraint on the curvature of space was extracted from light emitted by matter we will never interact with again. The most important data set in all of cosmology comes from a source that is already a ghost. We built our understanding of the universe's age, composition, and geometry from photons sent by matter that slipped beyond the event horizon billions of years ago. The information arrived. The source vanished. We are studying messages from a sender who has moved permanently beyond the reach of any reply. The ghost fraction is not shrinking. It is growing. Galaxies that today sit just inside the event horizon, just close enough that their current emissions will eventually reach us, are being pushed outward by accelerating expansion. Every year, the event horizon claims new territory. Galaxies that were reachable yesterday are unreachable today. The census of our causal universe is declining in real time, not because galaxies are being destroyed, but because the space between us and them is being manufactured faster than light can cross it. The universe is not losing matter, it is losing connections, and each lost connection represents a permanent reduction in the fraction of reality that will ever be accessible to any observer in our cosmic neighborhood. What determines how fast this isolation proceeds is the behavior of the one force that controls the expansion rate. Dark energy governs the speed at which the cosmic event horizon evolves, and its behavior over the coming billions of years will decide whether the isolation stabilizes, intensifies, or, in the most unlikely but not yet excluded scenarios, eventually reverses. The fate of every connection between our cosmic neighborhood and the rest of the observable universe depends on what dark energy does next. And the honest answer, as of the mid-2020s, is that we do not fully know. The rate at which this isolation proceeds depends on the behavior of dark energy. If dark energy remains constant, a true cosmological constant with unchanging energy density, then the cosmic event horizon will gradually approach a maximum distance of roughly 17 billion light-years and stay there. The loss of galaxies from our reachable sphere will continue, but eventually stabilize. The universe beyond the event horizon will expand forever, growing ever more remote, but the event horizon itself will settle into a fixed boundary. If dark energy strengthens over time, the isolation accelerates, the event horizon shrinks, the reachable universe contracts, and the process of cosmic disconnection intensifies. In the most extreme version of this trajectory, sometimes called the Big Rip, the acceleration would not merely carry distant galaxies beyond the event horizon. It would eventually overwhelm gravity on every scale. First, galaxy clusters would unbind, their member galaxies scattering into the expanding void. Then individual galaxies would lose cohesion, their stars drifting apart as the expansion rate within the galaxy exceeded the gravitational pull, holding it together. Then stellar systems would disintegrate, planets torn from their orbits by the stretching of space within the solar system itself. Then atoms would be ripped apart, the expansion finally overwhelming the electromagnetic force that binds electrons to nuclei. In the final moments, the fabric of space-time itself would tear, ending the universe not in cold silence but in a catastrophic shredding of every structure at every scale. Current observations do not favor this scenario, but neither do they rule it out. The dark energy spectroscopic instrument results, which hint that dark energy may be weakening rather than strengthening, suggests the opposite trajectory, a universe in which expansion gradually slows, potentially extending the event horizon over time. But the data are not yet conclusive. The future of the cosmic event horizon remains uncertain, contingent on the behavior of a force we do not understand. What is certain is the long-term trajectory of cosmic isolation. On timescales of tens of billions of years, the night sky will thin. Galaxies currently visible at the farthest reaches of telescope sensitivity will redshift into invisibility, their light stretched to wavelengths too long for any conceivable instrument to detect. Closer galaxies will follow, one by one, their recession velocities exceeding the speed of light as accelerating expansion carries them beyond the event horizon. The Virgo cluster, the nearest major concentration of galaxies outside our local group, will cross beyond the event horizon within approximately 100 billion years. The great superclusters Laniakea, the Shapley concentration, the sprawling filaments of the cosmic web will dissolve from view over similar timescales. Within roughly 2 trillion years after the Big Bang, the only galaxies visible from our cosmic neighborhood will be the few dozen members of the local group, the Milky Way, Andromeda, Triangulum, and the small dwarfs gravitationally bound to them. By that time, the Milky Way and Andromeda will have long since merged into a single elliptical galaxy, sometimes called Milkomeda. This merged galaxy will be the dominant structure in the local group, a massive island of stars surrounded by an ocean of expanding emptiness. Every other galaxy in the cosmos will have been redshifted beyond detection, erased from the observable sky by the relentless stretching of space. Imagine a civilization arising in that future cosmos. Their astronomers point their telescopes outward and see nothing. No distant galaxies. No cosmic web. No evidence that the universe contains anything beyond their local group. The cosmic microwave background, the afterglow of the Big Bang that provided our generation with the key to understanding cosmic origins, will have been stretched to wavelengths so long and energies so low that no instrument can detect it. The evidence for the Big Bang itself will have been erased. The evidence for cosmic expansion will have vanished because there will be no distant galaxies receding to measure. The very data that allowed 21st century humans to discover that the universe is expanding, that it began in a hot, dense state, that it contains dark matter and dark energy, and billions of galaxies arranged in a vast cosmic web. All of that data will be gone, carried beyond every horizon by the expansion those future astronomers cannot see. Those future scientists would have no reason to believe the universe was ever different from what they observe, a single galaxy floating in an apparently static, apparently eternal void. They would develop cosmological models that bear no resemblance to ours, because the evidence for our cosmology would have been systematically destroyed by the very process we discovered. They would be scientifically rigorous, methodologically careful, and completely wrong about the nature of the universe they inhabit, not because they made mistakes, but because the cosmos hid the truth behind an expanding horizon. Think carefully about what those future astronomers would actually see. Their galaxy, the merged remnant of the Milky Way and Andromeda, surrounded by a handful of small satellite dwarfs, would contain several 100 billion stars, aging slowly as stellar fuel runs down. Star formation would have largely ceased, because the available gas would have been consumed or expelled over trillions of years. The night sky from a planet in that galaxy would be filled with stars, their own galaxy's stars, but beyond those stars, nothing. No faint spiral shapes, no distant clusters, no cosmic web. The sky beyond the galaxy's edge would be black in a way that no 21st century astronomer has ever experienced. Not the blackness of empty patches between galaxies, which our instruments can fill with faint background light. True blackness. The total absence of any detectable photon from any extragalactic source. Their telescopes would be powerful. Technology does not necessarily decline over cosmic time, and a civilization surviving for trillions of years might develop instruments far beyond anything we can currently imagine. But no instrument, however sensitive, can detect photons that do not exist. The light from distant galaxies would not merely be faint. It would be gone stretched to wavelengths longer than the observable universe of that era, with individual photon energies lower than the quantum noise floor of any conceivable detector. The cosmic microwave background, which in our era bathes the entire sky in a faint glow at a temperature of 2.725 degrees Kelvin, would have cooled to a temperature so close to absolute zero that it would be indistinguishable from the quantum vacuum itself. The afterglow of creation would have faded below the threshold of physical detectability. Without the cosmic microwave background, those future scientists would have no evidence that the universe was ever hot, dense, or opaque. Without distant galaxies, they would have no evidence that space is expanding. Without redshift measurements from receding objects, they would have no way to discover the Hubble flow, no way to infer dark energy, no way to reconstruct the expansion history of the cosmos. The entire evidential foundation of Big Bang cosmology, the framework that tells us the universe began 13.8 billion years ago in a hot, dense state and has been expanding ever since, would have been erased, not suppressed, not hidden by complexity, erased, physically and permanently, by the very expansion that the framework describes. What would those scientists conclude instead? They would observe a single galaxy in an apparently static void. Their galaxy would not appear to be moving relative to anything, because there would be nothing else visible to move relative to. They might conclude that their galaxy has existed forever, an eternal island of stars in an infinite, changeless emptiness. They would develop physics that describes stellar evolution, nuclear reactions, gravitational dynamics, all with perfect accuracy within their galaxy. They would be brilliant scientists. Their models of local physics would be correct, but their cosmology, their picture of the universe as a whole, would be completely, fundamentally wrong. They would have no creation event, no expansion, no primordial nucleosynthesis, no dark energy. Not because these things did not happen, but because every piece of evidence for them would have been carried beyond the cosmic event horizon and destroyed by redshift. This scenario illuminates something unsettling about our own position. We assume that we live in an era of sufficient evidence that the data available to us is enough to reconstruct the true history and structure of the cosmos. The cosmic microwave background is detectable, distant galaxies are visible, the expansion rate is measurable, the evidence exists, and we are collecting it. But the Dark Era thought experiment reveals that the availability of cosmological evidence is not a permanent feature of the universe. It is a temporary condition, specific to our epoch, contingent on the accident of living early enough in cosmic history for the relevant signals to still be detectable. We happen to exist during the window in which the universe is willing to show its hand. This raises a question that has no comfortable answer. If future civilizations can be systematically misled by the absence of evidence that has been carried beyond their horizon, is it possible that we are being misled in the same way? Are there signals, phenomena, or structures that existed in the early universe but have already been erased by expansion before we could detect them? Is our current cosmological model as successful and well-tested as it is built on a data set that is itself incomplete in ways we cannot recognize? Because the missing evidence was destroyed before we developed the instruments to look for it? There is no way to answer this question definitively. The very nature of the problem is that missing evidence leaves no trace. If a signal has been redshifted beyond detection, we cannot know it was ever there. If a structure existed beyond our particle horizon and was never visible to begin with, we cannot know it existed. Our cosmological models are the best explanations consistent with the data we can collect. But the data we can collect is limited by horizons that are not transparent. They do not merely hide distant objects. They hide the very fact that those objects exist. We are in a better position than the Dark Era astronomers. We can see billions of galaxies. We can detect the cosmic microwave background. We can measure the expansion rate and infer the existence of dark energy. Our window is open far wider than theirs will ever be. But the window is still a window. It frames a view, and the view is bounded. What lies outside the frame is not empty, it is simply unseen. And the boundary between seen and unseen is not fixed. It is moving, slowly, steadily, inevitably, in the direction of less. None of this is speculative fiction. The scenario that cosmologists call the Dark Era is a straightforward consequence of the measured acceleration of cosmic expansion, and requires no new physics, no exotic assumptions, no speculative leaps beyond what current data already support. The isolation of our local group is as inevitable as the aging of stars, a process already underway, already measurable, already shaping the future of every observation we will ever make. This window is closing, not abruptly, not catastrophically, but steadily. As the event horizon trims away the edges of the accessible universe, galaxy by galaxy, filament by filament, photon by photon, the map we are building right now, the most complete map of the cosmos that any civilization in our local group will ever be able to construct, is the best map there will ever be. It will not improve indefinitely. It will eventually shrink as the universe withdraws its evidence behind an accelerating curtain of expanding space. But there is something even more important embedded in the structure of these horizons that most discussions of cosmic size overlook entirely. The horizons do not just limit what we can see, they limit what we can know. The observable universe is not the whole universe. The particle horizon and the cosmic event horizon define boundaries of observation and causal contact, but they say nothing about what exists beyond them. The cosmos almost certainly continues past the event horizon. Space does not end at 16 billion light-years. Matter does not vanish at 46.5 billion. The laws of physics do not change at the boundary of the observable sphere. These horizons are artifacts of our position in space-time and the finite speed of information transfer, not features of the universe's actual structure. This distinction between the limits of observation and the extent of reality is the most consequential idea in this entire story. Most people, when they hear that the observable universe is 93 billion light-years across, unconsciously treat that number as the size of the universe. They imagine a sphere of space 93 billion light-years wide, and they picture its edge as the place where the cosmos stops. But the observable universe is not the universe. It is the part of the universe that has had time to communicate with us. It is a window, not a room. And the room may be enormously, perhaps infinitely, larger than the window. The existence of cosmic horizons means that there is a hard epistemic limit on what any observer can learn through direct observation. We cannot see beyond the particle horizon. We cannot send signals beyond the cosmic event horizon. We cannot, by any physical means currently understood, acquire information about the universe beyond these boundaries. And if the total universe is much larger than the observable universe, as every major cosmological model predicts, then the overwhelming majority of reality is permanently hidden from us. Not temporarily hidden, the way a ship beyond the ocean horizon is merely out of sight. Permanently hidden, the way a region of space beyond the cosmic event horizon is causally disconnected from our future for all of eternity. How much larger the total universe might be is a question that takes us beyond what horizons alone can answer. Horizons tell us where observation stops. To ask what lies beyond observation requires different tools, measurements of cosmic geometry, the physics of inflation, statistical inferences drawn from the shape of space itself. These tools do not offer certainty. They offer constraints, lower bounds, probabilistic estimates. But the answers they suggest are extraordinary. The universe beyond the horizon is not merely a little larger than the observable sphere. By even the most conservative estimates, it dwarfs the observable universe by factors that strain the capacity of mathematical notation to express. The horizons are real. The limits they impose are permanent. The isolation they guarantee is inevitable. But the question that matters most, how much of reality is hidden behind them, requires looking at what the shape of space itself reveals about the size of the cosmos we can never directly see. You are standing in a warehouse so vast you cannot see its walls. You hold a flashlight. The beam extends outward into the darkness, illuminating dust motes and distant shelving for as far as the light can reach. Beyond the beam, everything is black. You know the warehouse continues past the edge of your light. You can hear echoes returning from far beyond what you can see, and the floor beneath your feet shows no sign of ending. But you cannot determine whether the warehouse is twice the size of your beam, 1,000 times larger, or whether it extends without limit in every direction. Your flashlight defines the boundary of your knowledge, not the boundary of the building. The observable universe is that flashlight beam, and everything cosmology has learned in the past century suggests that the warehouse is incomprehensibly larger than the circle of light we can see. The most direct evidence for this comes from the shape of space itself. General relativity allows the universe to have one of three possible large-scale geometries. Space can be positively curved, bending back on itself like the surface of a sphere, in which case the universe is finite and has no edge travel far enough in a straight line, and you return to where you started. Space can be negatively curved, flaring outward like a saddle, in which case the universe is infinite. Or space can be flat, neither curved inward nor outward, in which case it may be infinite or it may be finite with a more complex topology. But either way, it extends far beyond anything we can observe. Determining which geometry describes the real universe is not a philosophical exercise. It is a measurement problem, and one that the Planck spacecraft tackled with extraordinary precision. By analyzing the angular size of temperature fluctuations in the cosmic microwave background, tiny hot and cold spots that correspond to density variations in the infant universe, scientists can determine how light has traveled across cosmic distances. In positively curved space, light paths converge, making distant objects appear larger than they would in flat space. In negatively curved space, light paths diverge, making distant objects appear smaller. In flat space, light travels in straight lines, and objects appear exactly the size that their distance predicts. The Planck mission's final results, combined with baryon acoustic oscillation measurements, constrained the curvature parameter omega k to a value of 0.001 plus or minus 0.002. This is consistent with perfect flatness. Space, as measured across the full diameter of the observable universe, 93 billion light-years of traversable geometry, shows no detectable curvature whatsoever. The margin of error is less than 0.5%. If the universe curves at all, it curves so gently that the entire observable cosmos, vast as it is not large enough to reveal the bending. This result has enormous implications for the total size of the universe beyond the observable horizon. If the universe was small, comparable in size to the observable sphere, measurable curvature would almost certainly appear. A universe only slightly larger than the observable volume would curve enough for the Planck satellite to detect. The fact that space appears perfectly flat across 93 billion light-years means that the total universe must be much, much larger than the portion we can see. How much larger depends on assumptions, but even conservative estimates are staggering. A team of researchers led by Mihran Vardanyan at the University of Oxford performed a Bayesian statistical analysis of cosmological data, combining measurements from multiple sources to determine the most probable lower bound on the total size of the universe. Their conclusion was that the universe is at least 75 times wider than the observable universe in every direction. This places a lower bound on the total diameter of approximately 7 trillion light-years, a volume so enormous that the entire observable universe, with all its 2 trillion galaxies and its hundreds of billions of trillions of stars, would fit inside the total cosmos the way a single coin fits inside a football stadium. The observable universe would not be a significant fraction of the whole, it would be a rounding error, and this is the conservative estimate, the one derived from measurement and statistical inference without invoking any specific model of the early universe. The moment you incorporate inflation, the leading theoretical framework for explaining why the universe looks the way it does, the numbers become almost impossible to express. Cosmic inflation is the hypothesis that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially accelerating expansion so violent that it dwarfs anything happening in the cosmos today. In a sliver of time, almost too brief for mathematics, to comfortably describe roughly 10 to the negative 36th of a second, the universe expanded by a factor of at least 10 to the 26th power. A region of space smaller than an atomic nucleus was stretched to a volume larger than the entire observable universe is today, in less time than it takes a photon to cross a single proton. Inflation was proposed in the early 1980s by Alan Guth and independently developed by Andrei Linde, Alexei Starobinsky, and others, to solve several deep puzzles about the observed universe. Why does the cosmic microwave background look so uniform in every direction, even though widely separated regions of the sky should never have been in causal contact? Because inflation stretched a tiny, causally connected patch of space until it encompassed everything we can now see. Why is the universe so flat? Because inflation stretched any initial curvature until it was undetectable, the way inflating a balloon to enormous size makes any small patch of its surface appear perfectly flat. Why do we not observe exotic relics predicted by particle physics, like magnetic monopoles? Because inflation diluted them to undetectable densities by expanding the volume of space so rapidly that any pre-existing particles were spread across a cosmos too large to search. Inflation explains these observations with remarkable economy. It has made testable predictions, particularly about the statistical properties of the temperature fluctuations in the cosmic microwave background, that have been confirmed by satellite measurements. It is not a proven fact. It remains a theoretical framework with several competing variants and unresolved questions, but it is the leading explanation for the initial conditions of the observable universe, and it carries implications for total cosmic size that are almost beyond comprehension. To understand why inflation produces such extreme size estimates, you have to internalize one critical fact about exponential growth. Inflation was not linear expansion. It was not the steady, gradual stretching that the universe undergoes today, where space grows by a tiny fraction of a percent over millions of years. Inflation was exponential, a process in which the universe doubled in size, then doubled again, with each doubling taking the same incomprehensibly brief interval of time. The total number of doublings determines the final size. And with exponential processes, small changes in duration produce enormous changes in outcome. Think of it this way. One doubling takes a tiny region of space and makes it twice as large. 2 doublings make it 4 times as large. 10 doublings make it roughly 1,000 times larger. 20 doublings produce a factor of roughly 1,000,000. 30 doublings produce a factor of roughly 1,000,000,000. Each additional doubling multiplies the total size by 2, and the multiplication compounds on itself. By the time you reach 60 doublings, which is approximately the minimum number required for inflation to solve the flatness problem, the horizon problem, and the magnetic monopole problem, the original region has expanded by a factor of roughly 10 to the 18th power. That is a billion. A patch of space smaller than a proton would have grown to a volume vastly larger than the entire observable universe. 60 doublings is the minimum. It is the floor, not the ceiling. And this is where the sensitivity becomes almost frightening. If inflation lasted for just 10 additional doublings, 70 instead of 60, the universe is not 10% larger. It is 1,000 times larger in every linear dimension. 1,000 times wider means 1,000,000,000 times greater in volume. The difference between 60 and 70 doublings, a difference of perhaps 10 to the negative 37th of a second in actual elapsed time, multiplies the total volume of the universe by a factor of 1,000,000,000. If inflation lasted for 80 doublings, the universe is 1,000,000 times wider than the 60 doubling version. If it lasted for 100 doublings, the universe is 1,000,000,000,000 times wider. If it lasted for 120, the number exceeds any quantity that human language has standard words for, and every one of these durations is physically plausible. Current observations can determine that inflation lasted at least long enough to produce the observed flatness and uniformity of the cosmic microwave background. They cannot determine how much longer it continued beyond that minimum. The extra duration is invisible to us, because all it did was create more universe beyond our horizon space. That is real, that presumably contains the same kinds of structures and matter we observe locally, but that lies permanently outside the reach of our particle horizon. This is the core of the problem. The total size of the universe depends exponentially on a parameter, the duration of inflation, that we cannot measure. We can place a lower bound on it. We cannot place an upper bound. The observable universe tells us inflation lasted long enough. It cannot tell us whether inflation lasted 1 doubling longer, or 10, or 100, or 1,000. And each additional doubling multiplies the total cosmos by a factor of 2 in every direction, compounding relentlessly on the already incomprehensible size produced by all the doublings before it. This is why cosmologists who work with inflationary models routinely describe the total universe in terms that sound absurd. They are not exaggerating for dramatic effect. They are reporting what the mathematics says. When a model predicts a universe with a diameter of 10 to the 12th power centimeters, that number is not an arbitrary guess. It is the result of plugging a specific and entirely reasonable inflation duration into the exponential expansion equation and reading off the answer. The number is monstrous because exponential growth is monstrous. It is the same mathematical process that makes compound interest powerful over decades and pandemic growth devastating over weeks, except applied to the fabric of space itself over a duration so brief It makes the blink of an eye look like a geological era. If inflation expanded a subatomic region by a factor of 10 to the 26th power in a fraction of a second, and if the total duration of inflation was even slightly longer than the minimum needed to solve the flatness and horizon problems, then the universe that emerged from inflation is not merely larger than the observable volume. It is larger by a factor that requires towers of exponents to express. Some inflationary models predict a total universe with a diameter measured in numbers like 10 to the 10 to the 12th power centimeters, a number so large that writing it out in standard notation would require more digits than there are stars in the Milky Way. In these models, the observable cosmos, 93 billion light-years of galaxies, voids, filaments, and clusters is smaller than a single subatomic particle relative to the full extent of inflated space. Not figuratively, not as a poetic exaggeration, as a straightforward ratio of volumes. It is important to state clearly what is established and what is inferred here. The flatness of space is measured. The Planck data are confirmed. The lower bound of 250 times the observable diameter is a statistically robust inference from real data. These are observations and well-supported conclusions. The inflationary models that predict vastly larger sizes are theoretical. They are consistent with observations. They solve real problems, and they make confirmed predictions. But the specific claim that the total universe is 10 to the 10 to the 12th power centimeters across is model dependent. Different inflation models give different durations and different expansion factors. The shortest plausible inflations produce universes only modestly larger than observation requires. The longest produce universes that stretch toward infinity, and infinity itself remains on the table. If the universe is perfectly flat, exactly flat, with zero curvature, not merely flat to within measurement error, then standard cosmological models permit the universe to be spatially infinite. An infinite universe has no edge, no boundary, no total size. It extends without limit in every direction. Every finite observable sphere, no matter how large, would constitute 0% of an infinite cosmos. The question of whether the universe is truly infinite or merely so large that its curvature is unmeasurable may be permanently unanswerable. The difference between a universe with a diameter of 7 trillion light-years and one that is genuinely infinite has no observational consequence within the particle horizon. Both would look identical from inside our flashlight beam. Some cosmologists have explored the possibility that the universe might be finite, but have a complex topology, a shape that wraps around on itself in ways that would be detectable if we looked carefully enough. In a universe shaped like a three-dimensional torus, for instance, light could travel all the way around the cosmos and return to its starting point, creating repeating patterns in the cosmic microwave background. Researchers have searched for these patterns in the Planck data and found none. If the universe does wrap around, it wraps on a scale larger than the observable volume, meaning the topology is hidden beyond our horizon, just like the curvature. Every path of inquiry leads to the same conclusion. Whether through direct measurement of curvature, statistical analysis of cosmological data, inflationary modeling, or topological searches, the evidence converges on a single picture. The observable universe is a small, possibly infinitesimally small fraction of the total cosmos. The edge of the observable universe is not a wall. It is not a boundary where space ends. It is a horizon of knowledge, defined by the speed of light and the age of the cosmos, beyond which the universe almost certainly continues in ways we can describe theoretically, but never confirm observationally. This brings us to the deepest implication of cosmic size, the one that separates this story from a simple accounting of large numbers. The universe is not merely bigger than most people realize, it is bigger than observation can ever prove. The total cosmos may extend for 7 trillion light-years, or 7 quadrillion, or 7 times infinity. And from inside the observable sphere, all three possibilities would look identical. The particle horizon limits what we can see. The cosmic event horizon limits what we can reach. And both of those horizons sit far, far inside whatever the true extent of the universe may be. This means that the majority of reality, the overwhelming bulk of whatever exists, is permanently, irrevocably hidden from every observer who will ever live in our cosmic neighborhood. Not hidden the way a distant continent was hidden from medieval Europe. waiting to be discovered by better ships and bolder explorers, hidden in a way that no technology, no spacecraft, no signal, no instrument of any kind can ever overcome. The barrier is not engineering, it is physics. The speed of light is finite, the age of the universe is finite, expansion is accelerating, and together, these three facts guarantee that most of what exists will never interact with us in any way. We are accustomed to thinking of science as a project that, given enough time and resources, can eventually answer any question about the natural world. The history of human inquiry supports this optimism. We mapped the surface of the Earth. We charted the motion of planets. We decoded the structure of the atom, the sequence of the genome, the age of the cosmos itself. Every generation has expanded the frontier of knowledge beyond what previous generations thought possible. But cosmic horizons represent a different kind of limit. They are not barriers that better instruments will overcome. They are consequences of the structure of space-time itself. The speed of light will not increase. The age of the universe will not rewind. Expansion will not reverse. The information hidden beyond the horizon is not waiting to be uncovered. It is causally disconnected from us, as unreachable as the past, as inaccessible as the interior of a black hole. And here is where the story arrives at its most honest and most unsettling point. What we call the universe in ordinary conversation, the galaxies, the cosmic web, the microwave background, the vast surveys of billions of light years of structure is not the universe. It is the observable universe. It is the part that light has had time to reveal. It is the fraction of reality that happens to sit inside the flashlight beam. Everything we have ever measured, every data point in every cosmological survey, every photon collected by every telescope ever built, comes from inside a sphere that may constitute less than 1 part in millions, or billions, or numbers too large to write, of the total cosmos. The map is not the territory, and in this case, the map may be an unimaginably small scrap torn from a territory whose full extent is forever unknowable. This does not diminish what cosmology has achieved. The fact that a species confined to a thin biosphere on a small rocky planet orbiting an ordinary star in an outer spiral arm of one galaxy among trillions has managed to determine the age of the cosmos, the composition of its energy budget, the geometry of its space, the history of its expansion, and the temperature of its oldest light to within fractions of a percent, is one of the most extraordinary accomplishments in the history of organized thought. The observable universe is not small. It is staggeringly, incomprehensibly vast. 93 billion light-years of structure, containing hundreds of billions of galaxies, each harboring hundreds of billions of stars, many orbited by planets of their own. The sheer quantity of matter and space and time encompassed by the observable volume dwarfs every other scale humans have ever encountered. But the terrifying revelation is not that this volume is large. It is that this volume may be essentially nothing compared to what lies beyond it. The particle horizon is a circle of lamplight in a warehouse whose walls we have never seen and may never see. The cosmic event horizon is closing, trimming that circle smaller with every passing moment, withdrawing galaxies from the future of observation one by one. And the warehouse, the total universe, the full extent of whatever space and matter and structure exist beyond every horizon, may be so large that no analogy drawn from human experience can do it justice. Not grains of sand, not drops of water, not atoms in the earth, the observable cosmos, in its entirety, may be a smaller fraction of the total universe than a single atom is a fraction of the observable cosmos. Or it may be smaller still, or the comparison may not even be meaningful, because the total universe may be infinite. We do not know. We cannot know. And the reason we cannot know is not that our instruments are too weak or our mathematics too crude. It is that the universe has arranged itself so that most of its content is permanently beyond the reach of light, the only messenger that could carry the information we need. The speed of light, the finite age of the cosmos, and the accelerating expansion of space conspire to create a situation in which the overwhelming majority of reality is observationally silent present, presumably in the same way that the ocean beyond the horizon is present, but offering no evidence of its existence that we can ever collect. The universe is far bigger than you think. Not because the numbers are larger than you expected, though they are. Not because the distances are longer than you imagined, though they are. The universe is far bigger than you think, because the part of it that you can think about, the part that light has shown you, the part that science has mapped, the part that telescopes have revealed, is a tiny, bounded, shrinking window into something that may have no boundary at all. What we call the universe is really the part of the universe that has had time to speak to us. The rest is silence, and the silence may be vastly, perhaps infinitely, larger than the voice. Every photon that arrives at a telescope tonight carries information from inside the particle horizon. Every galaxy and every deep field image sits within the observable sphere. Every measurement in every cosmological survey samples the flashlight beam, and everything that matters for our understanding of reality, its age, its composition, its structure, its fate, has been determined from this one small sample, this one circle of light in the darkness. We have assumed, because the evidence supports it, that the universe beyond the horizon resembles the universe within it, that the same physics applies, the same structures form, the same laws govern the behavior of matter and energy. This assumption is reasonable, but it is an assumption, too, and it may be wrong in ways we cannot test, because the universe beyond the horizon can never be observed, never be measured, never be interrogated by any experiment we can design. This is the true meaning of the title. The universe is far bigger than you think, not as a statement about large numbers, but as a statement about the limits of knowledge. The size of the cosmos is not just an impressive figure to be recited and marveled at, it is a challenge to the deepest assumptions of scientific inquiry. The cosmos, it tells us that we live inside a horizon, that most of reality is hidden, that the map we have built is brilliant and precise and almost certainly incomplete by a margin so vast it defeats comprehension. What lies beyond the horizon may be more of the same, or it may be something entirely different. The honest answer, the one that cosmology, at its best, is brave enough to give, is that we do not know. The universe is not just enormous. It is enormous in a way that places most of its content beyond the reach of the only tool light that could ever tell us what is out there. We see a sphere. Beyond the sphere, there is almost certainly more. How much more? We may never learn. And that uncertainty is not a failure of science. It is the universe telling us, in the clearest possible terms, that reality is not obligated to fit inside the beam of our flashlight. The light reaches as far as it can, the rest is darkness, and the darkness may go on forever.